Hello and welcome to part 2 of our review for Common Exam 3. We continue with number 5. Determine whether the series are absolutely convergent, conditionally convergent, or divergent, and state which test you are using. So the first one we will do is limit comparison theorem. Okay, if we take absolute value here, we're going to say an is just n over square root of 4n cubed plus 1. And then for limit comparison, we're going to say bn would be n over the square root of n cubed. Now the square root of n cubed would be n to the 3/2, which if we were to reduce this would come out to 1 over n to the 1/2. Okay, so that's our bn. Now that's important because we know that 1 over n to the 1/2 by a p-series with p equaling 1/2 is less than 1. So this is a divergent series. So that's important to note. Okay, that'll come in handy later on. So for limit comparison theorem, we will do, for limit comparison test, I should say, we will do a limit as n approaches infinity of a to the n over b to the n. Okay, so let's start from there. Okay, so we have limit as n approaches infinity of n over square root of 4n cubed plus 1 divided by bn. Now divided by the 1 over n to the 1/2 is the same as multiplying by n to the 1/2 over 1. Okay, so when we multiply n times n to the 1/2, we have n to the 3/2 over square root of 4n cubed plus 1. Okay, so now if I divide everything by n to the 3/2, so here I would divide by n to the 3/2. Now this term is inside the square root, so I could just divide inside by n cubed. Okay, that'll act like being divided by n to the 3/2. So we have the top part equaling 1. Remember, we still have a limit. Top part equals 1. Bottom part inside the square root, we would have 4 plus, and then the 1 over n cubed, that would go to 0. So we have 1 over square root of 4, which is 1/2. Okay, so this 1/2, this is our limit, and the limit is greater than 0. So we would say that because bn diverges by the p-series, then an would diverge by the limit comparison theorem. Okay, now because of the -1 to the n in the beginning, we're going to also test by the alternating series test. Okay, so alternating series test, we have to show that the series is decreasing, all the an's are positive, and if the limit approaches 0 as n approaches infinity, then we could say that we have a conditionally converging case. So let's see. The first part, we're going to try to show that we have the an's are decreasing. Remember, one of the methods for this was taking the derivative. So by alternating series test, and taking the derivative, of our ANs. So taking the derivative would be, now obviously we're not dealing with the -1, we're just taking absolute value. So the derivative of n over square root of 4n cubed plus 1. So that means we have the denominator, so square root of 4n cubed plus 1 minus numerator times the derivative of the denominator, so that would be n times 1/2 4n cubed plus 1, drop the power, -1/2, times the derivative of the base, so that's times 12n squared, all over denominator squared, which is 4n cubed plus 1. Okay, we have to show that this derivative is less than 0. Okay, and you can go through this. You'll see that you have this square root of n cubed, so this is like a n to the 3/2 power term here, and then here we have an n squared times the n, so that's an n cubed over an n to the 3/2, so that's another n to the 3/2 when you reduce it. Okay, but you have a n to the 3/2 minus 1/2 of 12, 6. So this is going to end up being a negative on top for n's going to infinity. Okay, so therefore we could say that an is decreasing. And then we see that the ANs are all positive. That was another condition of the alternating series test. And then we have to take the limit, final step, as n approaches infinity of our AN. So n over square root 4n cubed plus 1. Okay, so here, when we take the limit, what I could do here to simplify this a little bit, I'm going to divide by n, and when I divide by n here, it's like dividing by n squared, because I'm going inside the radical. So this top part gives me 1. The bottom part gives me 4n. Well, this goes to 0. Okay, so as I go n going to infinity, the square root of 4 times infinity would be infinity. So I'd have 1 over infinity, which as we get larger and larger, we see that this is 0. Okay, so therefore we would say that this converges conditionally by the alternating series test. Okay. All right, let's take a look at the next part. So for the part B, again we have another alternating series here with the -1 to the n. Here we could try the ratio test. Okay, so remember what the ratio test was. we would take the limit as n approaches infinity of absolute value a n plus 1 over a n, and this would give us rho. And so if rho turned out to be less than 1, it absolutely converges. If rho is greater than 1, it diverges, and if rho equals 1, it's inconclusive. Okay? So, alright, when we take absolute value, we have basically n over e to the n. Right? Another way to write this would be n over e to the n. Okay, so if we do a sub n plus 1, that would be n plus 1. So we have limit as n approaches infinity of n plus 1 over e to the n plus 1 times, now I'm going to divide by a sub n, but instead of dividing by this fraction, multiply by its reciprocal, so multiply by e to the n over n. Okay, so another way to write this is if we have n plus 1 over e to the n times e, right? We can split up e to the n plus 1 as e to the n times e, and then we can cancel. We can cancel the e to the n's. We have e to the n and e to the n. Okay, so let's continue further. So that means then we have limit as n approaches infinity of n plus 1 over e times n. Okay, and then what I could do here, so next we can divide everything by n. Okay, so we're left with 1. This will go to 1. This will go to 0. N's will cancel here and give us e. So 1 plus 0 is 1. And then over e. So 1 over e. Now 1 over e. E is about 2.718. And it continues. 1 over 2.7. That's less than 1. Right, and the rule was if rho was less than 1, then we absolutely converge. Okay, so therefore, absolutely converges by the ratio test. Okay, so that's 5b. Let's take a look at our next problem. 6a. Write down the first three non-zero terms of the Maclaurin series for the function f of x equals 2x e to the x. Okay, so it helps if you know what e to the x is. Right, if you know what e to the x is, it makes things a whole lot easier. Remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial ... Now we only need the first three non-zero terms, so we're going to focus on these three, the first three non-zero. So we have 2x times e to the x. Okay, so picture 2x here in front. So we're going to basically do 2x times e to the x. So 2x times 1 plus x squared over 2 factorial. Okay, what does that give us? It gives us 2x. We could just distribute. 2x times 1 is 2x, 2x times x is 2x squared. 2x times x squared would be 2x cubed. Okay, we could simplify that a little bit with the 2's here. 2 factorial, 2 times 1 is also 2. Okay, so final answer then would be 2x plus 2x squared plus x cubed. Okay. Alright. Next, find the first three non-zero terms in the Taylor series about a equals 1 for f of x equals 1 over x. Okay, so we need the first three non-zero terms. Okay, so we need to first come up with our function, our derivatives, and then we have to evaluate at 1. Right, so we have f of x. For the first term would be 1 over x, and we plug in 1 because we have a equals 1, so plug in for x equals 1. That's from our a equals 1. So 1 over 1, we get 1. Okay, then we have the next term is the first derivative. First derivative of this would be negative 1 over x squared. Plug in 1, we get 1 squared is 1, so negative 1. Okay, the next one will be the second derivative. Second derivative of this would be now positive 2 over x cubed. Plug in the 1, so we get 2. Okay, and that's all we need. So now let's plug into our Taylor series. And it's about a equals 1. So the first one would be, we take the coefficient here, it would be 1. And then for the next term, it would be a negative 1, so we have a minus x minus 1. Next will be a positive 2, so put plus 2, and then x minus 1 squared over 2 factorial. And so we could simplify again between the 2 and the 2 factorial. So final answer here, we have the 1 minus x minus 1 plus, and then show this, these two cancel, plus x minus 1 squared. Okay, so those will be the first three non-zero terms. Okay, let's take a look at number 7. Find the radius of convergence and interval convergence for the following series. Okay, so we will use the ratio test. Okay, so remember the ratio test. Limit as n approaches infinity, an plus 1 over an, and that equals rho. If rho is less than 1, converges absolutely. It's greater than 1, diverges, equals 1, inconclusive. But we're going to use the converges absolutely part to figure out our radius and our interval convergence. Okay, so let's take the limit. Okay, so we got limit as n approaches infinity. So we have x plus 3 to the n plus 1 power over n plus 1 squared times 2 to the n plus 1. That would be divided by the original an. Now divided by that would be multiplied by its reciprocal. Okay, so multiply by n squared over 2 to the times 2 to the n over x plus 3 to the n. Okay. So keep in mind the x plus 3 to the n plus 1 power. That means that we have x plus 3 times x plus 3 to the n over n plus 1 squared. And then for 2 to the n plus 1, we could split that up and say 2 to the n times 2 times the reciprocal of our original an. Okay, now some things will cancel, right? We have x plus 3 to the n, that cancels. We have 2 to the n cancels with 2 to the n. Okay, so we have what do we have here? We have x plus 3. Keep that in absolute value. We have underneath a 2. And then here we have n squared over n plus 1 squared. And keep in mind you still have limit as n approaches infinity. Okay, so if you apply the limit as n approaches infinity, you'll see that the n squared and the n plus 1 squared, this is really an n squared for the bottom, right? We have n squared plus 2n plus 1. This is going to go to 1. You basically have n squared, you divide everything by n squared, right? And then you see that this goes to 1. Okay. So that means all we're left with is really this piece here. So we're going to say that absolute value of x plus 3 over 2, and because we're trying to show the interval of convergence, and we know that rho, when it's less than 1, it converges absolutely. So we'll say absolute value x plus 3 over 2 is less than 1. Okay, now we multiply both sides by 2. Okay, so when it's in this form, this number is your radius, right? So that 2 there, that's your radius of convergence. So keep that in mind. Okay, so now we set this up just like an absolute value inequality. We would say negative 2 is less than x plus 3 is less than 2. And then we subtract 3 on all 3 sides. So we end up with negative 5 is less than x, which is less than negative 1. And for the interval of convergence, now we have to test what happens when x is both of these numbers. Right, so for the first case, when x equals negative 5. Okay, so let's go back into our original series. When n equals 1 to infinity, we plug in negative 5 for x. Negative 5 plus 3 to the n over n squared times 2 to the n. Okay, this simplifies. Negative 5 plus 3 is negative 2 to the n over n squared 2 to the n. Okay, so here the negative 2 to the n and the 2 to the n, we could cancel there. We'll be left with a negative 1 to the n. Okay, so we have absolute value summation n equals 1 to infinity of negative 1 to the n over n squared. Okay, so we know that the summation, right? So we know that the summation n equals 1 to infinity of 1 over n squared, this converges. By the p-series, right? It's a p-series, n equals 2, which is greater than 1. So therefore, the series when x equals negative 5 converges. Okay, converges absolutely. Now let's look at what happens when x equals negative 1. So when x equals negative 1, so we have negative 1 plus 3 to the n over n squared times 2 to the n. Okay, so this simplifies to negative 1 plus 3 is 2 to the n over n squared 2 to the n. 2 to the n's will cancel, so we have summation 1 over n squared. Okay, so we know that this converges, right? It's a p-series. P equals 2, which is greater than 1. So therefore this series converges. So to answer the question, going back to right here, this was our radius 2. Alright, so our radius is 2. And our interval of convergence, we get the square bracket on the negative 5, and we get the square bracket on the 1, because they converge at both of those, and then we're done. Okay, next, let's take a look at number 8. Determine whether the series is convergent or divergent. Please state which test you're using. Okay, so when I see this raised to the n power here, okay, that gives me a good indication that I could take the root test. Okay, so remember the root test. We would take the limit as n approaches infinity, and we would take the nth root of the absolute value of a n, and this would equal rho. And the rule was, if rho is less than 1, it converged absolutely. If rho was greater than 1, diverged and if rho equals 1, it's inconclusive. Okay, so let's take the nth root here then. We got the nth root of n sine of 2 over n to the nth. Okay, so we see clearly that the nth root and the nth power, they will cross out. Epsilon of n sine of 2n is itself. So we take the limit as n approaches infinity of n sine of 2 over n. So now I'm going to rewrite this as we have sine of 2 over n, and times n I'm going to do divided by 1 over n. Okay, because what I'm going to do next is I'm going to take L'Hopital. Okay, so you're going to take L'Hopital, take the derivative top and bottom. Okay, so if we take the derivative of top and bottom, we end up with, we have cosine of 2 over n times the derivative of the base, so that would be times 2 over n squared. Derivative of 1 over n is negative 1 over n squared. Okay, we have the negative 1 over n squared and the negative 2 over n squared, for the most part, will cancel. We'll be left with a 2 up here. Right? The two negatives will cancel. So we're left with a 2. So we have limit n approaches infinity of cosine of 2 over n times 2. So now think what happens as n approaches infinity. As n approaches infinity, 2 over infinity goes to 0. So we basically have cosine of 0 times 2. Now cosine of 0 is 1, and then 1 times 2 is 2. So our rho equals 2, and the condition was if rho is greater than 1, we get a divergent series. Okay, so therefore we would say diverges by the root test. And then that would be it. Okay. Any questions you guys have, just write me an email. Alright. And just keep studying this. Anything that pops up over the weekend, write me an email. So have a good day, have a good night. We'll see you soon.